floor is yours, Judith.
Thank you. Yeah, thank you very much for the nice introduction. My name is Judith Michael. I'm a postdoc at the Chair for Software Engineering of Bernhard Rumpe at RWTH Aachen. And it's a great pleasure to present research we are doing together with Malte, Nico, Christian, Florian, and Bernhard about deriving language families. And I'm happy to being able to share our experiences with you in this talk. Now, why should we care about language families at all? If we think about the complexity of the world, we have, for example, energy systems with different entities, technologies, and stakeholders involved. Or if we think about production systems, which is a main area we're caring about in Aachen with our colleagues from mechanical engineering, where you have complex life cycles, materials, processes, and server physical production systems. Or also in the transportation systems, where you have different participants, technologies, or sensory information that you have to handle. You have very complex systems where you have different perspectives and heterogeneous information that you need to handle. And we think that one method to handle this complexity is to use different domain-specific languages. But this requires us that we are integrating the different perspectives that we have, the viewpoints that we have, and also the purposes that different stakeholders might have when they are using these different languages. This leads us to an increasing number of domain-specific languages covering these different domain concepts that we need. And from a research perspective, it's especially interesting that we further analyze how we can foster reuse as one of the good best practices that we have in software engineering to increase the quality and productivity that we have when creating domain-specific languages. The main research question we tried to further elaborate within this paper is how we are able to integrate different modeling languages via different language composition techniques that we apply to achieve such multi-viewpoint modeling languages. And clearly, we use a certain technology space. I will not provide you the full details of the slide, which Nico has already given you in session 2. Just the main aspects which are interesting here from this technology. Montecore enables the fast and easy engineering of domain-specific languages, and it allows for reuse. We especially support different language composition techniques, and it allows us to define modular language fragments. And those are the main functionalities that we are using now within the next slides. For the easy and fast engineering of domain-specific languages, we have established 3 different layers of languages in Montecore. On the base layer, we have different kinds of language components which can be which are reusable, and those can be full or just partial components. And to give you a little bit more insights into this feature diagram shows the main set of these language components, where we have basic types, we have basic symbols, expression basics, and the literal basics. I think one of them has even not found the place on this slide because I got it too late. Basically, if you want to have more details about it, you can find the grammars and the details on GitHub and also in some of our publications. The basic principle that we have behind these language components is that we created them to be most reusable in different kinds of languages. So for example, we have here this SE unit types for math and the one for computing. One of them allows us to define, for example, meters per second speed, and the other one meters per second double speed, where we also have this type information. This is something which might be not interesting for physicists if they would use such a language component. So we have here 2 different kinds of components that could be integrated in domain-specific languages. And I'm quite sure this feature diagram will increase in future if we find also additional language components that could be reused also for other projects. On the second layer, we are talking about domain-specific languages, so fully functional domain-specific languages with a specific focus. This could be, for example, different UML languages like class diagrams, object diagrams, state charts, or also other kinds of languages. And on the third layer, we are talking about different language families. We also call them multi-viewpoint languages because they enable us to cover different perspectives of a system. And especially this layer is now where we want to focus on in this talk. So to reach this layer, we want to reuse what is already existing, which is basically both the language components, but also complete languages that we already have created. And we still want to be able to maybe add something new or redefine parts of the languages that we have already created or the components. Therefore, we have to rely on established language composition mechanisms to create these larger language families. I will give you a short overview of the 4 different language composition mechanisms we apply here. The first one is inheritance. So here we are using an original language, and we are extending the new language as an extension of this existing one. Now, what is interesting about this new DSL is here we can still adapt and extend or modify concepts that we have used, created in this first language. So you have an example here where we have extended the class diagram language. We are using the CD class non-terminal and overwrite it. We change the terminal here from class to entity. Now, if we would create a model from this language, it would has entity, then the brackets, then a list of attributes, and another bracket. This is a non-conservative extension. So it means models that we might have had from this language 1 at the beginning are not valid anymore if we use this new kind of language, which we have composed using language inheritance. The other more conservative kind of language composition is language extension. So here we are creating a new DSL, but the existing elements can only be modified or extending in a non-restrictive way. With this kind, we are making sure that the models of the original language, so the language L1, are still valid when we have this language extension. You have an example here, again, a class diagram language, where we are again overriding the non-terminal CD class and add a new CD method. This CD method enables that we include method signatures into the class bodies of our already existing language, which means we have both models without the method signatures and models with model signatures, which are now valid in this new language. And yeah, you can find other details about that in the paper. The third language composition mechanism we are talking about is language embedding. This is interesting if we want to integrate multiple domain-specific languages, so we have not just one language, we have several of them, and we combine their production rules in a single grammar. You have here as an example where we use the automata language together with the common expressions which we embed in this language. This results in a new grammar for a mealy automata. And in line 4, you can see that we are able to import additional artifacts and advance the normal automaton that we had to a mealy machine, which enables us to process an input and producing a corresponding response action. The last mechanism, I will not go into detail because I think Nico has already talked about language aggregation. So basically here we have still the different artifacts of the languages which can be kept as different artifacts, but we ensure via the symbol table that we have a loose coupling between them and that the different models are able to work together in a whole system of languages. Now, when we're talking about modeling languages, we can't use very simple examples because that's not fun. So we have brought with you 2 larger language families that we have created over several years now in different projects. One of them is the Multi-Things language family, which has the aim to simplify the development of IoT applications. We have created an MDE approach for that, for the design, development and analysis of such IoT applications. And the interesting part of it is that it enables lifecycle support, which means you can start at the beginning in an iterative development approach from prototyping to deployment of the whole IoT system until its operation within using a digital twin for monitoring functionality and also supporting maintenance, for example, with error identification during runtime. This was especially developed by Christian, so you can find out more details in a quite long PhD thesis, which is already available, but also some other publications which we had at Modelers Gypsy and in the JSS journal. What is behind that is a language family, which is based on a component connector architecture description language, which we use to generate C++ code for distributed applications, as well as scripts for the container packaging that we're able to deploy the system. We can also supplement the generated code or overwrite it with handwritten extensions, which are basically given by Montecore, and its functionality of the top mechanism. And together with this core functionality and core languages, we have also added other kinds of languages, like for configuring models for hardware or software platforms, defining tests, and other kinds of languages. The second large language family that we have used as a use case is the Assist language family. That's basically a large part of my research. So here we have the aim to simplify the development of assistive systems. And if we talk about assistive systems, we aim to provide human behavior support. It could be in different kinds of situations, like for manual assembly and production, to driving, or to activities in daily life. This is not only interesting for old people, because basically when everybody of us is stressed, we're also forgetting some things we should do, or we're forgetting routines. And if you're doing new things in a job, you need training to follow certain processes, so it could be used for different kinds of systems. The idea is to support such assistive systems with using MDE approaches, and we use the MontiGem generator to develop web applications together with a language family, either to generate large parts of this system with a domain model, a language for graphical user interfaces, and also OCL to generate the core part of the application. And we have created two additional languages, the context language to include objects during runtime, and the task language to include processes, and both of them are basically natural language based, so that people without software engineering skills also understand the concrete syntax of these languages. Now let's have a look into the different composition scenarios one could find when we are defining domain-specific languages. The first scenario is based on one domain-specific language. So if we modify a language and tailor it to a specific use case, which means we are creating a new domain-specific language and use another one as a base language, we could apply both inheritance as well as language extension mechanisms. In inheritance, it's interesting for us if we have, for example, no former models that we want to reuse, and it's already clear that we need our new tooling anyways and can't really reuse the tooling that we had before. Extension, here it's more interesting if we are able to reuse tooling and might not need very domain-specific concepts which are not covered in the existing language. The second scenario is when we extend a language to a use case while still maintaining the integrity of the original models. So here clearly language extension is more suitable because this makes us, gives us the possibility to still reuse existing models. Here it is important that the language workbenches that we use ensure that we keep these modifications really conservative, so that they also provide warnings if you're doing other things which you shouldn't do. Now, the first two of them were about using just one domain-specific language. The third scenario here, we are also talking about language components. So the scenario would be to combine different language components into a domain-specific language. Here, suitable method is, for example, embedding. This is effective when the DSLs share common interfaces. It also means that no glue code is necessary, and a prerequisite to do that in a good way is that your DSL developers are aware of the language components which exist, that they know what to reuse in a meaningful manner. What is not suitable in this case is, for example, language aggregation, because it would be just a loose coupling, and you can't use the components into a fully functional DSL without adding additional information. The fourth scenario, here we are talking about already more than one domain-specific language we have to handle. So we want to combine different domain-specific language into a language family. They are already fully functional languages. Here, both embedding and aggregation would be suitable. It really depends on the use case. If we want to have integrated views where for the users of these models, they have embedded information already in one model, not caring about if there are different DSLs behind it, or if you want to keep separate artifacts. The same basically also occurs for scenario 5, where you want to construct huge domain-specific languages with different constituents. Here, the aim is that you support the organization and structuring of larger modeling projects. Again, both embedding and aggregation is possible, but it really depends on the use case, which of these methods is then more interesting for you. The sixth scenario we're looking at is to construct a large language family with heterogeneous parts for interdisciplinary use. This requires that we have interdisciplinary teams which are using the models and modeling language later on. And here the artifacts presents different domain-specific visions on a system. Therefore, aggregation is very suitable in this case because it enables domain experts that they have views in these different kinds of models without getting distracted by information from other perspectives, so you can have very focused information for very specific stakeholders. Partially suitable would also be language embedding. And the last bigger scenario we can have a look at is the modularization of model artifacts, especially if you work with domain-specific languages over a longer amount of time. You'd start to modularize your languages more and more. Here we do that because we want to have a separation of concern and also create a suitable modeling project structure. For this approach, only aggregation is a suitable composition method. Now, if we look into the bigger two large language families that we have in our paper, you can see already in MontyThings that different of these scenarios would apply. MontyThings is composed of 46 grammars of the Monty-Core project, with reusing more than 4,000 lines of code of these grammars. And for example, it reuses the Monty-Arc language, which you can see here, but in a non-conservative way. So it is extended, for example, for error handling, but some of the constructs had to be refined. We are extending the statements, for example, and using that in MontyThings. We are reusing existing components, like here for the SE units, for example, but also parts of the OCL project. And we have, for example, the class diagram project here, which we use for defining complex data structures. So, for example, so that we import symbols via language aggregation here. You can also see that it was getting a very huge language, so we also had to start to think about modularization here again for MontyThings itself, but also for the configuration language, for example. If we look into the other language family, the Assist language family, here we have languages to generate the system on the right, and we have the context language and the task language, so they're both with a concrete syntax based on natural language text here in the middle. We have, for example, a conservative extension for these SE units when we found out that it would be interesting if you have, for example, a cooking and recipe support that you need tablespoons and other units which are not existing in the SE unit projects. We are also reusing a lot of the language components which are already provided by Montecore itself. When we are using these units, they are directly embedded, for example, into the context language. Here we are using language embedding as a method. We can also use concepts of the context language within the task language via language embedding. Again, we have class diagram information as separate information for types, and also this enables us to have different views for different roles. Because basically these parts here are more technically focused, and in the context language we have this more natural language-based view for the users. And we also modularized the language over time into different kinds of language components, so like these article and direction components were taken out of the context language after some time. And you also see that there are some further plans to change the language, for example, that we are reusing the BPMN language and extend it for the different kinds of task types, specific task types that we need here. But this would still enable us to reuse tooling which is already provided by the BPMN language then in the longer run. Now, you have seen it's a lot of different kinds of techniques and methods if you're working in larger language projects. Here you can see an overview of the different scenarios. You can also find them in a paper. And what we have seen is that the more sophisticated the language becomes, the more likely it is that we apply a more elaborated approach. This means methods like inheritance and extension is typically used if we keep the scope within a single domain or a certain use case. And when it comes to embedding or aggregation, those are typically the techniques that we are applying for multi-viewpoint modeling and also for larger language projects. Now, I hope I have shown you a little bit more about how to capture complex systems using different kinds of techniques and how to enable language families by using embedding and aggregation possibilities. You can find more details in the paper, and I'm happy to answer your questions.
Thank you very much, Judith, for the presentation. So, is there any questions in the room? We have plenty of time for the Q&A session.
Thank you for your talk. I was wondering, when defining the feature diagram for language families, one of the most critical parts is that when requirements evolve over time, over the years, you may need to change the feature diagram, and then the language implementation must match the new version of the diagram, so they are always kept aligned. So my question is, did this problem happen during the years working with language families? And if it did, how did you manage it? And maybe if you ever considered doing a bottom-up approach in which the feature diagram is extracted automatically from the language implementation rather than the other way around.
You're referring to the feature diagram for the language components, or?
Yeah.
I think basically we just use that for presentation here on this slide. Yeah.
Oh. I think if you can use a mic in that case.
So basically it was just a graphical representation here for the feature diagrams. So we are not using the feature diagram language to represent language components. They're independent language components, but the feature diagrams shows how they could be used with the different relationships that they have between each other.
So as a follow-up question, then the composition is handled in a programmatic way, not at a model level, right?
Yes, it's done at the grammar level, not at the model level, basically. If you're really doing changes in the grammar itself, you have to also care about model evolution. For that, we also have applied some techniques to identify how the models should be changed and can be changed, but this is something which is up to research right now.
Okay, thank you very much.
There was another question, yeah, Thomas?
Yes, thank you for the presentation. I would suspect that in many cases, the quality of the small language components influences a lot what you can do with them. So basically, it's the problem of how to break down a language. If you start with a big language and you try to break it into different pieces, there is an infinite possibilities to choose the individual components, and depending on how you do it, it will be easy or not to recompose the entire language. So did you ever face the situation on these two language families where you thought that you should use a particular composition operator because this is the one that's the most, that's the best for the scenario that you have, but the components that you have do not match? And they're just really hard to compose together because they were not designed in the proper way.
I would say up to now we did not have the problem that the components did not match together. What is a problem is if the developers are not aware that the components exist and they still develop their own methods then within the grammar itself without reusing a component. But this is something which you have to do then afterwards in a, let's say, stabilizing phase of the grammars itself, so that you have more experienced developers who can give you feedback on that and say, maybe you shouldn't have done it that way, but you should have included the language component which already exists. And it was also, I would say, in last times when we had to change the grammars towards that, quite easy, because you have the integration mechanisms of the language components, and it's quite easy to, get that part out of an existing grammar and take the language component instead in this grammar. So that's, I would say, a very practical approach also for developers. Like you would lose a library in a programming language, for example.
Okay, thank you.
Any other question? So I can ask mine in the meantime, Judith. So looking at the paper during your presentation, you seem to distinguish composition operators that are based on grammar versus model, which is probably more meta-model than model, by the way. And I was just wondering, what is for you the pro and cons of having composition operator on grammars or versus meta-model? I mean, is there any pro and cons, and what are the benefits of one with regard to the other ones?
Basically not. I think you could also establish such operators also on meta models. Yeah.
No specific.
No specific reason for that.
Okay.
No.
Is there a last question in the audience? No. So it's probably time to conclude. Yeah, please, Andreas. Go for the last one.
Thank you for the talk, Judith. I'm wondering if you would continue this line of work, how would you go on to find new composition scenarios to validate this framework?
I'm not sure if much more composition scenarios exist. If they exist, I think we would also need examples from industry where they have also larger language families. There are some companies out there who have created their own language families, which I know, and I think that could be an approach where we could get additional examples from. Based on the ones I think that we have covered, at least for the academic world, hopefully all scenarios, which might be interesting from different complexity levels. But yeah, so I think we would need other examples from industry for that.
Thank you.
Thank you very much. So this concludes our session. Thank you very much, Judith. I think we can give a big applause to